So the topic, dear students, the topic that has been that I'm going to discuss with you is soft computing approaches for engineering applications. So you're all computer science students, I understand. So we'll just start with a basic introduction about what is computing. So can any of you just tell me, according to you, what is computing or according to you? What do you have in mind when I say computing? Yes. Okay, I'm sorry. So, in simple words, like computing means you're mapping a given set of inputs to outputs using a formal method, or let's say an algorithm, to solve a problem, right? So this input, sometimes we call it as the antecedent, and the output we call it as the consequent. For example, suppose you give an antecedent as x, so you have a function y is equal to f of x, and you get a consequent function y, right? So this method of computing, this has to be unambiguous, it has to be accurate, and it has to give you a precise solution. And it is suitable only for problems that you can model mathematically. So actually, it was Cse, he was the first person to introduce a concept of hard computing. And according to him, a computing concept comes under the category of hard computing if it can provide you with a precise result, the algorithm used to solve the problem is unambiguous, and the control action is formally defined using an algorithm or a mathematical model. So all the problems that we do in class during like finding the derivative, finding the integral, or finding the shortest path between 2 points, or sorting, finding the largest number of an array, all of these comes under hard computing problems, because always you get a precise result out of it. Okay, you get an accurate and precise solution out of it, and you always have a mathematical model. So those are all qualified under hard computing. Then what exactly is soft computing? So this class will be mainly on soft computing. So from hard computing, let's move on to what is soft computing. So the real world tasks that we see around, for example, handwriting recognition, image classification, music generation, they don't have an algorithm, right? And they don't give you an exact solution also. So this is where soft computing comes into play. So the term soft computing is coined by, again, Cse. He's also called Icet. He defines soft computing as follows. He says, soft computing is a collection of methodologies and aim from the tolerance of imprecision and uncertainty to achieve tractability, robustness, no solution cost. Its principal components are fuzzy logic, neurocomputing, and probabilistic reasoning. And the role model for soft computing is a human mind. So we saw some keywords over here. We saw some keywords. What are the keywords? We saw imprecision. We saw uncertainty. We saw robustness. We saw low solution cost. What are these terms? What do they mean? So you all know tolerance of imprecision, which means that the result that you get from a soft computing algorithm, it need not be precise. Okay? Uncertainty. It does not give you the same answer each time. You execute an algorithm, you may get a different answer the next time. Robust. It can pattern of input noise. It usually, using soft computing techniques, they are actually computationally very expensive if you try to solve them using hard computing techniques. And basically, they're inspired by, as we said earlier, it is based on the human mind, so it is inspired by biological decision-making systems, and it follows methodologies like genetics, evolution, and behavior, particle swarming, human nervous system, etc. So basically, soft computing, we've got 3 paradigms. It is fuzzy logic, we have neural computing, and we have probabilistic reasoning, like you have genetic algorithms, particle swarm optimization algorithms, and things like that. So in this particular lecture, we'll be discussing about one particular topic, that is, we'll be discussing about fuzzy logic in detail. So we'll start with an introduction to fuzzy systems. So before we begin, some very clever people have said in the past. What have they said? Precision is not truth. They said precision is not truth. Albert Einstein says, so far as the laws of mathematics refer to reality, they are not certain. And so far as they are certain, they do not refer to reality. And coming back to Lance, he says, as complexity rises, precise statements lose meaning and meaningful statements lose precision. Confused. I gave a lot of statements. So here everything is talking about precision and its meaning or its significance. He says precise statements lose meaning and meaningful statements lose precision. So let me give you a daily life example so that you will understand what is precision and what is significance. So here you can see two people standing there, right? So suppose it's you and your friend. There's a person A and a person B. Person B is standing in one particular place. You can see a huge thing is going to fall on his head. So what does person A do? So person A, his friend who's standing next to him, you have person B on whose head the thing is going to fall. So person A tells him, does he tell him like this? A 1,500 kilogram mass is approaching your head at 45.3 meters per second. Do you say that? Or do you just say, look out? What do you say usually? You say just look out, right? So their precision doesn't have any importance. Is it important for person B to know that how much kilo mass is coming and what velocity is coming? It's just important to convey the information that you have to move out of that place. Or let's assume that you are crossing the road and suddenly there's a vehicle that is approaching you from behind you. You have not seen that vehicle. So a standby person, a person who is standing there, he sees you, he sees the vehicle and you, and he just says, what does he say? He says, watch out. He doesn't tell you that this model of car is coming from behind you at this particular speed. Doesn't tell you all that, right? So in real world, actually, it is significance that has not got more importance, and it's not precision that has got more importance. Similarly, everything that happens in the world around us is having a fuzzy nature. So let's see, what is fuzzy about everything in the world? So if you see the words and evaluations we use in our daily reasoning, they're not clearly defined in a mathematical manner. For example, let me ask you, I'm sure you are all in college today, you will be attending a conference. How is the temperature at Thrissur now? Can anybody tell me? How is the temperature? Okay. So suppose I ask you, what is the temperature issue? Telling me it is cold, or you would say it's cool, or you would tell me it's hot. You are telling me that is 30 or 30, I'm saying not 36, 20 degrees Celsius or 29 degrees Celsius. Don't tell me all that, right? You just tell me that the temperature is a particular value. That's what you tell me. So what's important there is not the crisp value or the precise value. You just tell me related to it's cool here. Or let's say, similarly, suppose I ask you in a class of let's say 20 students, I ask you to tell me how for tall. So some people assume that people who are 160 centimeters and above are tall. But whereas for some other people, tall means 170 centimeters and above. So there is a relative perspective also there. Right. So most of the words in evaluations, it's not clearly defined in a mathematical manner. So suppose I tell you from a set of 20 students sitting in a class, you create a subset of students whose height is 6 feet and tall, 6 feet and above. In that case, you can easily pick up some students. Out of 20 students, you get 15 students who are 6 feet and above. Suppose you get 15 students, fine. So that is one way of doing it. But then there's a problem. A student whose height is 5.99 does not qualify in it. Whereas a student whose height is, let's say, 6.01 feet, he qualifies into that set. So, is that correct? Okay. So, in real life, everything has some fuzziness element. So, what we do is that we are going to give a varying degree of membership to such things. So, a fuzzy logic is actually a way of representing this variation or imprecision in logic. So a person, it can be a two-valued logic wherein that person, if you take a person, let's say a particular person, let's say a boy called Nikhil, you call him. So if he is 6 feet and above, if he is above 6 feet, he is a member of that set. So that is two-valued logic. It's either yes or no. Whereas in that's Boolean logic or two-valued logic. Whereas in fuzzy logic, we give this particular person a varying degree of membership into that set. We can say he's more or less tall or he's quite tall. Okay, he does not qualify in very tall, but he qualifies in tall. So he has got a varied degree of membership. So fuzzy logic is actually a way to make use of natural language in logic. For example, when you talk about temperature, we use some linguistic variables. What are linguistic variables? Instead of telling the temperature is, let's say, 30 degrees Celsius, we say the temperature is freezing, the temperature is cool, the temperature is warm, the temperature is hot. So these are called linguistic variables. Or when you're talking about cloud cover, you would say it's overcast, or you would say it's partially cloudy, or we would say it's sunny. Or if you're talking about speed, you would say slow, fast, fastest. And even that we communicate with others, even our reasoning is also approximate reasoning. Like we say, if it is sunny and warm today, I will drive fast. Okay, if it is sunny and warm today, I will drive fast. So our reasoning is also approximate reasoning. We are not saying that if the temperature is this particular value and then I will drive at this particular speed. We don't say that. We just give an approximate reasoning wherein we say if it is sunny and warm today, I will drive fast. So fuzzy logic is a logic underlying such approximate rather than exact modes of reasoning. In bivalent logic, truth is bivalent. Like we said, it's either true or false. You don't have varying degree of truth allowed. For example, let me give you another example. Suppose you take a person who is, let's say, 30 years old. Okay, and would you put him, you have got three sets, suppose, a set of young people, a set of middle-aged people, and a set of old people. So suppose you have a person, let's say X, who's 30 years old. Which set should you assign him to? Should you assign him to the young set or the middle-aged set? Or let's say 35 years old. So you may be assigning him to a young set with a low degree of membership, but then you will assign him to a middle-aged set with a higher degree of membership. That is not possible in bivalent logic because either he can be a member of set or he has to be a member of the young middle. It is an extension of multi-valent logic where everything is a matter of degree. Let's say 35 old, he is, let's say, 30% young age set and more than 70% middle age set. Something like that. So that's actually what happens in fuzzy logic. Each variable gets a very degree of membership in the sets. So many decision-making problem-solving tasks, like most of the things that we have in the real world, we are not able to model it mathematically. So it's difficult for us to create mathematical models and do compute technique. When suppose I ask you where you got the image of chair and asked you to tell it, can you do it? That's very difficult. But that you can easily do using using artificial neural networks or support vector machines using some image processing techniques. Okay, with the support of these machine learning algorithms. So most of the decision making and problem solving tasks are too complex to be defined precisely, and people will succeed using imprecise knowledge. And fuzzy logic is basically wherein you resemble human reasoning and its use of approximate information and uncertainty. Idea about what is fuzziness in our real world. So just to understand what is fuzzy logic, I'm taking a layman example. Okay. Given the quality of service, how much should the tip be? So this is the example that we're going to take. So you have an input space, which is all possible service quality rating, and your output space is the tip that you're going to give. So you have been to a restaurant, you have had some food from there, now you want to tip your wait person, but you don't know how much to tip. So I'm going to design a black box which will tell me how much tip I have to give to the wait person. So given the quality of service, how much should I tip? Now this particular black box, it needn't be a fuzzy system, okay? It can actually be a neural network. You can even give a differential equation for it, or you can give an interpolated multi-dimensional lookup table or a linear system. Anything is possible here. Okay, but for now, let's see how to do it in fuzzy logic. So as a fuzzy case, fuzzy is faster and cheaper. So the same thing can be done using other things also. Because what is wrong for me cannot be wrong for you. Okay, so it's very flexible. I can adjust a membership function and I can change the value. It is tolerant of imprecise data. It can model nonlinear functions of arbitrary complexity. It can be blended with conventional control techniques, and it is based on natural language. So when not to use fuzzy logic? If you find fuzzy logic is not convenient, you try something else. If a simple solution exists, go for it. That's all. So for example, let us consider an example of controlling a fan. So in a conventional model, how do you control the fan? If the temperature is greater than a particular value, run the fan. Else, stop the fan. That's all. The same problem, if you were doing in fuzzy logic, you would write like this. If the temperature is hot, run the fan at full speed. If the temperature is warm, run the fan at moderate speed. If the temperature is comfortable, maintain the fan speed. The temperature is cool, slow the fan. The temperature is cold, stop the fan. So here, there are different linguistic terms you can see. There is hot, warm, comfortable, cool, and cold. So what is warm? So hot is not one particular value. It has got some value, some range of value. From this value to this value, you give a membership function. Similarly, speed. Speed has got very linguistic values. See, full speed, moderate speed, slow speed, stop. So different things you can do. So this is how you design a fuzzy system. So coming back to the earlier example about what is the right amount to tip your weight person. So given a number between 0 and 10 that represents the quality of service at a restaurant, where 10 is excellent, what should the tip be? So if 10 is excellent and 0 is extremely poor, how much are you going to tip the person? So very simple non-fussy approach to this problem would be, tip is always 15% of your total bill. Get the bill, whatever be the tip, just give 15%. Would you all do that? If you go to a restaurant, would you just give 15%? No, right? We look at some factors before we give the tip. What are the different factors we look at? We look at the service of the restaurant. We look at the quality of food. So these are two input variables that I can take into consideration when I decide the output. Which is the output in my case? It's a tip. What is the tip that I'm going to give? So my input here is two variables. What are the two variables? What is the quality of service? And the second variable that I'm going to take is what is the quality of food. So suppose I take only one variable at the first time, that is I'm taking only service, and service is rated, let's say, from 0 to 10. And you want the tip to vary from 5% to 25%. So if the service is bad, I'll give a 5% tip, and if the service is excellent, I'm going to give a 25%. So in a non-fussy, I will just write an equation. Tip is equal to service into 0.2 by 10 plus 0.05. So depending upon the value of service, I can decide the value of tip. This is a non-fussy approach. Okay? But suppose I want to include food also into it, not just service. I have to take my input, that is food. Again, food is also in a rating of 0 to 10, where 0 means very poor and 10 means excellent. Then again, I can just modify the equation as 0.2 by 20 into service plus food plus 0.05. This is a non-fussy way of doing it. But suppose I don't want to give equal weightage to food. I want to say that service takes 80% of the tipping and food takes 20%. What should the tip be? Again, I'm modifying the equation. See, ratio is equal to 0.8, okay? And then service ratio into 0.2 by 10 into service plus 0.05 plus 1 minus service ratio. I'm coming with that equation. What is the system like? Design what is the amount that you give. So whenever you have a fuzzy logic problem, what you have to do is you have to capture the essentials of the problem. You have to leave aside all the factors that could be arbitrary. What really matters in this problem is only important to you. So here what really matters to you is only the quality of service, quality of food, and you have to decide the tip. So first, let us take only the service factor into consideration. So I'm going to define 3 rules. My rule is, if the service is poor, then the tip is cheap. If the service is good, then the tip is average. If the service is excellent, then the tip is generous. Okay, so poor, good, and excellent. The tip is cheap, average, and generous. Now, to this, I'm going to add the food factor also. If food is rancid, then the tip is cheap. If food is delicious, then the tip is generous. So I've got 2 rules. A set of rules for service factor, a set of rules for food factor. Now what I'm going to do is that I'm going to combine it. So which are my 2 inputs? My input is service and food. And service has got three membership function. It can be poor, it can be good, it can be excellent. Similarly, food can be rancid or it can be delicious. And my output variable is tip. Tip can be either cheap or it can be average or it can be generous. So based on this, now what I'm going to do is that I've written separate rules for service factor and separate rule for food. Now I'm going to combine them together and I'm going to come up with an if-then rule. So when I combine them together, I will get if service is poor or food is rancid, then tip is cheap. If service is good or then tip is average, because it has nothing to do with here, there is no value called tip here. So if service is good, then tip is average. If service is excellent or food is delicious, then tip is generous. So these are my if-then rules that I have come up with. So this is how we think, right? In our minds, either the service is poor or food is bad, then you give a cheap tip. Okay? Service is good, you give an average tip. If service is very good or food is very delicious, then you decide that you give a generous tip. This is how we do it, rather than writing mathematical equations. Okay, this is how we normally think. So this is the contour map that the surface flaw I would get if I implemented in fuzzy logic. And I'll show you how I've implemented. I've done this problem in a simulation software called MATLAB. I'll just show you the result later. For now, I just want you to understand what a fuzzy logic modeling looks like. So now let's brush up some basics of fuzzy logic before we go on to the engineering applications of fuzzy logic. So a fuzzy logic starts with a concept of what is called a fuzzy set. A fuzzy set is a set without a crisp boundary. So it can contain elements with only a partial degree of membership. As I told you earlier, suppose you are given a set like this, a set which has got elements. Which are the elements? You can see that you can see shoe polish, you can see butter, you can see dorsal fins, you can see liberty. You can say Monday, Thursday, Thursday, and Saturday. You are asked to create a crisp set which shows the days of the week. It's a crisp set because this set has only 3 elements that are given there. It's Monday, Thursday, and Saturday. So this is classical set theory. Because it either includes something or excludes something. Each element is either a member of that set or it is not a member of the set. It's either true or false. It's binary logic. Okay, so there is either a true value or a false value. That's classical set theory. But in fuzzy set theory, this is now how it is. So suppose I create a fuzzy set. Now fuzzy set is you have to decide which day is a weekend. Okay, or what is the degree of weekendness. What is the degree of weakness? So let me ask you some questions. So in fuzzy logic, the truth of any statement becomes a matter of degree. Wait. is Thursday a weekend or like is Tuesday a weekend? No, Tuesday is not a weekend. It's Friday. Why? Weekend what is weekend? Eating. We are feeling weekend feeling. So we can say it was Monday is the weekend. No. What about Saturday? Sunday, that is the feeling has reduced from us, right? You're very complicated. Other things, other things. You're doing the things, okay? Monday is not a weekend, it's only Saturday and Sunday that's a weekend. So this is in true value membership or in logic. But in fuzzy logic, each day can have a varying degree of membership in the weekend. For example, Saturday is 100% weekend. But Sunday, I will not say 100% weekend because by evening, the feeling of weekend has started losing, starts losing. So I'm giving only, let's say, 95% weekend. Friday, I'm saying 85% weekend. By Monday, it has become 0. Okay, Thursday probably let's give some 40% because the feeling of weekend is approaching has come. Right. So this is how you have a fuzzy set and a normal crisp set. So each thing has a varied degree of membership when you come in a fuzzy set. So the membership of Friday is 85%. The membership of Saturday is 100%. Sunday is 90%. But here it's either 100% or 0% in two value membership function. So suppose I draw a curve that defines the weakness of any instant in time. Okay, then this is called a membership function. So weakness versus the day. So this is a membership function in two valued logic. Either it is 0 or it is 100. You don't have any intermediate values there. Either it is a 0 value or it is a 100 value. Whereas in multi-valued membership function, in fuzzy logic, you can have a varied membership function. See, Saturday 100%, but Friday, the value, if I take any time on Friday, okay, somewhere here, Friday, 3 o'clock, 4 o'clock, 5 o'clock, it has got a higher degree of membership. Friday morning, it's got a less degree of membership. So you can, this is such a plot is called the membership function. So I hope so far is okay. Any doubts so far? Am I clear?
It's clear, it is no problem.
So membership functions. So we saw membership function earlier, right? So a membership function is a curve that defines how each point in the input space is mapped to a membership value between 0 and 1. So the input space is referred to as a universe of discourse. Actually, it's a very fancy name for a very simple concept. It's a very simple concept. How do you say? So as I said earlier, I am defining a set of tall people. So in a crisp set, any person whose height is 6 feet and above, he becomes a tall person. Fuzzy logic, it's not like that. You can give a varied degree of membership into a set of tall people. So a person who's, let's say, 160 centimeter, I'll say more or less tall. 180 centimeter, very tall. Okay, so his membership value in the tall set will be high. Whereas a person with a height, let's say 160, his membership value will be less. So you can give a varied degree of membership. So here, this is a plot of the membership function for tall. Okay, so this person in two-valued logic, he is not tall. This person is tall. So either it is 1 or 0. But in fuzzy logic, what happens? You get a varying degree of membership. Okay, a person who stands here, he gets a varied degree of membership. Now, as I said earlier, when we said the service is poor or food is rancid, so when you want to combine two variables, you have to use some logical operation. So what was the example, our tipping example that I said? So I gave you 3 rules there. What was the first rule? The service is poor or the food is rancid. Then tip is what was it? Tip. This cheap. So here, you have fussy rules and connecting this fussy to have the logical difference. So you need to understand this logical difference. So in two logic, you know what data is 0, that is also can is 0. So it becomes 1, 3, 1. Maybe you have point so when you which actually found in the same way it's found we to an angle to it's all and we want to it's I'll show you some graphs. So in two-handed logic, if this is A, okay, and this is B, if you find out A and B, this is what you would get. A or B would look like this, not A would look like this. Whereas in fuzzy logic or multi-valued logic, if this one, the one you see here, this is A, and this lighter one, this grey colored one is B. Suppose you're asked to find out an AND operation, because then you have to find the minimum. At each point you find the minimum. So at this particular point, this is A, this is B. So what's the minimum value? Minimum values of B. So that is why you get a plot here. So this would come like this, okay, and then you would get a value. So this would be the membership when you find an AND operation. If you find an OR operation, every point you find a maximum. Whether A, whichever is maximum, that point you have to plot. So this is A curve, this is B curve. You find the maximum, you will get a curve like this. And negation operation or complement operation, this is A, just not A, would just be the 1 minus A. So this is how in fuzzy logic we use the logical operations of AND, OR, and NOT. So coming on to a fuzzy logic system. So in a fuzzy logic system, so this is basically the architecture of a fuzzy logic system. So you have some input variables, you have some output variables. So you are going to write some relationship between the input variables and output variables. But then the first step is the input variables are present as crisp variables. Okay, you have to fuzzify them, or you have to give them some membership function, and you have to make them fuzzy variables. For example, if your input variable is temperature, okay, then you have to give some linguistic values for temperature. For example, temperature you can say warm, cold, cool, hot. Okay, so 4 fuzzy values are given. And for each value, I have to give a membership function. For example, warm. Warm means, let's say, the temperature is from this particular range to this particular range. Or let's say cold. Cold, let's say it's from 10 degrees Celsius to, let's say 20 degrees Celsius is cold. I can give a bell membership function, or I can give a triangular membership function. Okay, so 10 means it's definitely cold. Okay, it's definitely cold. And then when I go towards 15, the cold value will decrease. So I can have a membership function that goes down. Okay, so like that, each variable that you have in the input space, you have to convert it to a fuzzy variable. So you also have some output variable. For example, in our case, tip and service, food and service were your input variables. You give some membership function. Your output variable was what? Output variable was tip. That also you have to give some linguistic variable. So we had 3 values, right? For tip, we had cheap. Then we had generous, we had average. So those were the membership values for the output. So for input service, we had poor, good, and excellent. And for food, we had delicious and advanced as a membership function. And for tip, we had 3 linguistic variables. Each one we have to give a membership function. Cheap, average, is generous. In between, we have this fuzzy inference system, which has a fuzzy rule base. What is a fuzzy rule base? We created 3 rules. If service is poor or food is rancid, then tip is cheap. If service is good, then tip is average. If service is excellent or food is delicious, then tip is generous. So that is what forms the rule base. So based on this rule, it will evaluate the rules on the two inputs and it will give you a value of it. Again, the value of it will be a fussy value. You will have to defussify it and you have to get a crisp value. I'll show it to you in So basically, a fussy inference system is the actual process of mapping from a given input to an so here function so linguistic way, what are the linguistic or thought? And then you what comes so now so basically there is a syntax principle. It's in the form of a quintuple. You will have it in the form x t of x capital X G M, where x is the name of the variable. So in this case, variable is h. P of n is the term set of x. That is set of all linguistic values, the linguistic terms. So for h, we can have okay. So x is age, P of x is young age, middle age, and young age, old age. And capital X is the universe of discourse. What is the value of x that can take? It can, let's say, vary from 0 to, let's say, 100. That's the universe of discourse. And G is a syntactic rule which generates the terms in T of x. How do you get T of x? What do you understand by young age? You have to define a membership function. So here I have defined a Bell membership function. So Bell membership function says that membership function young of x is equal to 1 by 1 plus x by 20 the whole raised to 4. So you give different values of x. You vary x from 0 to 100. Okay, you get some values for membership function. You plot it. It will be in the form of a Bell curve. Similarly, old, I'm giving a membership function 1 by 1 plus x minus 100 by 30 the whole raised to 6. So here again you vary x from 0 to 100 and you plot the values, you will get a Bell membership function. That is a membership function for old age. So T of x, this is the syntactic rule that generates the terms in T's. And then we also have a semantic rule which associates with each linguistic value its meaning, M of A. So here you have a set here, T of H. It's a fussy set which has got some linguistic terms. Young, not young, very young, middle age, less, very old, more or less old. I told you how to create old and young. But I didn't tell you how I can create not young. But not young, I know, by now you know. Because if this is young, to find not young, you just have to take 1 minus that. Right, you will get not young. Then how do you get very young or very old? Or how do you get very, very old? So for that also we have some operators in fuzzy logic. Those operators are, so here you can see, these are the operations that you can do on linguistic values. Concentration, A squared. Dilation, A raised to 0.5. Contrast intensification. So if the value of membership value is between 0 and 0.5, 2A squared. If it's between 0.5 and 1, minus 2 into A squared. So like that I can get negation. So for example, you can see this yellow curve, it is young. This is a bell-shaped function that I actually got by plotting in that equation that I gave you. This particular equation that I gave you. So in this, if you plug in different values of x and if you plot it, you will get a membership value like this. And this is for old age. Okay, so we have got two membership functions. Now suppose I want not young, what do you have to do? Not young is pretty easy for us because you just have to take 1 minus young. So not young would look like this, right? Start from here and it would go like this. Not young. Now, this is old. You can see old like this. How do you get extremely old? Extremely old you can generate as very, very old. And how do you get very, very old? For that, we can use this concentration. So just find A squared. So you want to it becomes extremely difficult, you will get this shape. So all these curves have been generated using the operations that are shown here. Okay? So this is not young and so this is and then you have to use the operator. So I use it should not young and old. Okay, means I am and then I'm using it young, but not young. Okay, so young, not young. Concentration based my brain. So to get membership functions of the fuzzy sets used so fuzzy what is the right stages? If tomatoes red, it is right. Real life using. If speed is high, then apply the brake a little. However, what given here, it is got only one antecedent, one consequent. This needn't be the case. You can have different values also here. If, as we said, if service is poor or food is rancid, you can have two variables. Then tapestry. And consequent also, you can have more than one. Okay. So then you have the inference engine. This is an inference engine wherein you're converting. If it is the first rule, second rule, third rule, you aggregate all the rules, get the fussy value, defussify, get the crisper value. So finally you have a defussifier. The defussifier converts the fussy output of the inference engine to crisp using membership functions analogous to the ones used by the fussifier. And there are some defussification techniques that we usually use. Centroid of area technique, center of sums technique, mean of maxima technique, smallest of maxima technique, largest of maxima technique. These are some of the defussifying techniques that are used in fussy. Again, actually, fussy inference systems are of two types. We have Mamdani type and Sugino type. Okay, so Mamdani inference is the most commonly seen inference method. It was introduced by Mamdani and Asilian in 1975. Another is Sugino or Tagaki-Sugino kind method of fussy inference system. And in both the cases, the initial part is the same. That is fussification, then generation of rule, all that is the same. The difference comes only wherein where you execute the consequent of the fussy rules. So in a Mamdani rule, the steps are the same. There are basically 6 steps that are followed. You determine a set of fussy rules, fussify the input using input membership function, combine the fussifying inputs according to fussy rules to establish a rule strength, find the consequence of each rule, combine the consequences, defussify the output. Okay, I'll just give you an example rather than reading all this. So here, there are two reasoning schemes that we usually use. One is maximum composition. Suppose you've got two input A and B, and your output is C. Okay, and then you have got two sets of rules. If X is A1, Y is B1, then output is C1. If X is A2, Y is B2, output is C2. And then you are giving one particular value for X. Okay, so here you are taking the minimum of this. So this and this minimum is taken and cutting the output here at minimum. This and this minimize taken. Then you aggregate the two outputs, so you get a system like this. Out of that, you take the maximas and then you defussify. This is called the maximum composition scheme. Or you can have a max product composition scheme also, where you take the product of these two, aggregate it, then defussify. This is called the max product composition scheme. So coming back to your earlier problem, the basic tipping problem, given a number between 0 and 10, it represents a quality of service at a restaurant, what should the tip be? So these are my inputs, service and food. I fussify the inputs. There are 3 rules. All the 3 rules will be evaluated in parallel. I will get 3 outputs. I will combine the 3 outputs. I will defussify it, and the output will be a non-fussy number. Look at this graph. For example, this is my first input, that is service. This is my first input, the 3 I can come see here. This is service and this is food. So service has got 3 values, 3 linguistic terms, poor, good and excellent. This is a membership function for poor. This is a membership function for good, and this is a membership function for excellent. Varies from 0 and 10. Okay, this value that starts as 0 and this is 10. So this is poor, this is good, this is excellent. Similarly, food varies from 0 to 10. Rancid food, this is no dependence. Delicious food. Okay, and then tip. I've got 3 membership function: cheap, average, generous. 3 membership function. Okay, varies from 0 to 25%. Then what I do is I've got 3 fussy rules. This is for food is rancid, then tip is cheap. Service is good, tip is average, no dependency on food. If service is excellent or food is delicious, then tip is generous. So now let's take one input. Input service is equal to 3. For triple, food is equal to 8 is your second input. So corresponding to 3, you draw a line. So here is for okay, food is equal to A. So here it intersects at 0. So here you have a membership function. Here it is 0. So I'm going to take max. So it's all operating. I'm taking the maximum. So suppose this is, let's say 30%, and here it is 0%. So point P from maximum is 0.3. This membership function sheet will be cut at 0.3. So 30% will be there. So you get a particular curve. Again, let's take the second one. Second is equal to 3, corresponding is equal to 3, I got some value. Let's assume 30% is what I'm giving. So thirdly, we got average at 30%. Again, like the third rule, this is equal to 3 comes somewhere over here. Here the membership value is 0. Food is equal to 8. The membership value is, let's say, 60%. So 0 and 60, maximum value is 60 or 0.6. So you cut here at 0.6, you get an output. Now you aggregate the 3. Okay? Combine the 3, you get something like this. Then what do? Defussify it. There are some defussification techniques. I told you, centroid method, center of sums method, maxima method. You defussify this. This will give you the value of depth. And for this particular value, that was what was the value? Service is equal to 3 and food is equal to 8. Fussy logic system told me that I have to give it a depth of 16.7%. So this is how fussy logic systems work. Now, just for you to enhance the understanding, let's take another layman example wherein you want to evaluate the health of a person based on its height and weight. So which are the 2 input variables? Height is one input variable, weight is the second input variable. And which is your output variable? The health of the person is the output variable. So output is percentage of healthiness. So input is height and weight. So what do you do first? The fussy inference system classification. You have to find some linguistic terms. So weight, I'm giving some linguistic terms. Very slim, slim, medium, heavy, very heavy. Height, very short, short, medium, tall, very tall. Okay. Then what do I give? I give some membership functions for weight. Slim, this is a membership function. Sorry, very slim. Anybody who's less than, let's say, 52. Okay. It's coming in this, but with varied degree of membership. Slim is, let's say, from 48 to, I don't know, this person has given it as 77. Medium, heavy, very heavy, some varied degree of membership. Then height is also put into some linguistic values, very short, medium, tall, and very tall. Now this again depends upon the user, okay? So you can define this. For what is slim for me may not be slim for you. So you can modify it accordingly. So these are the fussy variables that we created out of the CRISP variable. Okay, so this process is called fussification. Then you have to form some if-then rules. Okay, and you can adjust it. As and when required, you can adjust it, but then you have to tabulate it using fussy ones. Before that, you need the output, right? What was the output in our case? It was healthiness of that person. So a person can be unhealthy, less healthy, somewhat healthy, and healthy. So these are the fussy words that I've used. Again, for that also, I'm giving some membership function. Okay, unhealthy means it varies from 0 to 0.4. Less healthy is 0.2 to 0.6. So like this, I can give some values. Now I'm going to create my if-then rules. I've created in the form of a table. This is called a fussy rule table. Okay, so we've got 5 input variables and 5 output variables. So you will get 5 cross 5 matrix, or you can create as many as 25 rules from this. So here you can see very short, very slim is healthy. Very short, slim is somewhat healthy. Very short, medium is less healthy. Is very short and he's heavy. He's unhealthy. Very short and very heavy. It's unhealthy. So based on your logic, you can create a rule based like this, and then you can input that rule. Then you have to aggregate the rules, just like you did earlier. So, for example, let's calculate. Suppose the person's height is 185 centimeter and his weight is 49 centimeter. Then 185 becomes very slim and slim with very degree of membership. In very slim, he's 80%, in slim, he's 20%. Again, for height, he has got two values. Height is 185, so 185 here. So he comes in two. He comes in medium and tall. So he has got the membership in medium 70%. Right? All the case, if his weight is much and height is much, they are use one composition, maximum or max product composition, whatever you're using, and you get the detection, you will get the value is index of fussy decision, whether he's healthy or unhealthy. What is his percentage of healthy? Here, he's at 25% is in less healthy and 25% is in somewhat healthy. So this is the final decision. Okay. So why fussy logic? Again, I'm saying it's easy to understand, flexible, it is tolerant of imprecise data. It can model non-linear functions. It can be built on top of the experience of experts. It's based on natural language. I hope now you will appreciate how much it is based on natural language or the way we communicate. It can be blended with conventional control techniques. Now, till now what we saw was actually in the Manthani model. You can have a Sugino-Fussy model also, which was proposed by Tagaki, Sugino and Kan in 1985. So as I said earlier, it is very similar to the Manthani model. The first two parts are the same. The fussy inference process I thought I lost my connection. So, Sugino-Fussy model, it was proposed by Tagaki, Sugino and Kan. It is similar to the Manthani model in many respects. As I said earlier, is constant. It is the output membership function. It's either linear or constant. The input membership functions can be the same. So, for example, if x is a and y is b, then z, that is the output, is a function of x comma y. I'll give you some examples rather than giving the theory. For example, if x is small and y is small, then z is minus x plus y plus 1. If x is small, y is large, then z is minus y plus 3. So you have some relationships here. Rather than giving a varied degree of membership, some rules are given. So that is actually a Sugino model. Again, you have to fussify, apply the fussy operator, rest of it is the same. A reasoning scheme that we use here is actually a weighted average technique. We use weighted average technique as the reasoning scheme. When you compare a Sugino method and Tagaki method, actually Sugino method is computationally efficient and it works with your conventional linear technique like PID control. You can model any inference system in which the output membership functions are either linear or constant. It works well with optimization and adaptive technique. It is guaranteed continuity of the output space. It is suited for mathematical analysis. Whereas Manthani method is intuitive. It has widespread acceptance. It's well suited to human input, and formation of FIS is very, very easy. Now, coming on to some examples. So, this is one example that I did as part, I think it was in 2013, as part of one of my MTech students' project, was how to control the trajectory of a mobile robot using fussy logic. So, what I did was there was a reference trajectory that was given, and then the mobile robot has to track this reference trajectory. So the conventional techniques that we use were PID control, PI control and all that. But then the thought was to move towards adaptive control techniques or soft computing techniques because you don't have to model all the non-linearities when you're going for soft computing techniques. So that is why fussy logic was used in this particular project. So a reference trajectory is given. Your robot, which is a differential drive robot, has to actually track the reference trajectory. DC BLDC motor speed control. But then, being computer science students, I thought that it would be easier for you to understand mobile robot reference trajectory tracking when compared to BLDC motor, which is more has more of a electrical aspect. With some basic speed and torque and all. So, for example, so you get the quadratic operation of the mobile robot. The mobile robot was a differential drive robot, and then using some sensors took three variables. That was variable X position, Y position, and it was compared to trajectory. Error was given to the controller. So, P logic controller, and the physiological concept actually this is the input to mobile code. To track the trajectory. So this was the system that was developed. So actually, input waves that took X1 that displacement. This is from off the action of the trajectory. This is the angle. Okay, so this is an angle. Another basically the wheel velocity, the left wheel velocity, right wheel velocity. It was like near, medium, far, very far. For angle, I gave big negative, negative, zero, positive, big positive. And then for velocity, I gave very small, small, medium, very slow, slow, medium, fast, and very fast. And I gave some membership functions for all this. Okay, then I created a rule base, if then rules, 25 rules were there in this particular fuzzy inference system. An example I could tell you that if angle is big negative and distance is 0, okay, then velocity of the right wheel is very slow, velocity of the left wheel is very fast. Okay, and based on these rules, actually, the robot will change the direction and it will try to keep tracking the desired position. So these rules were created, and this was the rules of the right wheel velocity and rules for the left wheel velocity. And then this I had done in MATLAB. So this is a rule editor in MATLAB, wherein all the 25 rules were given. And here you can see the linguistic terms that were used for X1, for X2, for U1 and U2. And this was a fuzzy logic controller that was created in MATLAB. And this was my simulation setup. Okay. So this is my left motor plus wheel. This is my right motor plus wheel. Here I have the dynamic part of the robot, and then I have my sensors. And then here I have my reference trajectory generation, and then here I have my fuzzy logic controller. So the inputs are the distance and the angle, and then it will decide the left wheel velocity and the right wheel velocity. Okay. So these are actually the equations that I use for reference trajectory generation, and you can see the output. So first trajectory that I used was a curve like this. So this was my actual trajectory, that is this red one. And the reference trajectory was a blue one, and this is the actual trajectory that I got from my robot. So the robot can see was closely following the trajectory. And second case, I created a line as my reference trajectory. So initially the robot was at 0, 0 position, and this is how the line was going. Initially the robot deviated a bit, so it went like this, but then after some time it was able to catch up with the reference trajectory, and you can see the actual trajectory which is red and the reference trajectory which is blue, and you can see that they are on track. Okay, so this was one project that I did. Then I think I told you that I will show you the fuzzy inference system, right? So for that, I'll just share my slide once more. I'll just share MATLAB with you. So, is it visible? Can you see a fuzzy logic designer in MATLAB?
Yes, ma'am.
Okay. So this is that example that we were discussing from the beginning, a layman example, right? So here you can see this is actually a toolbox that is available in MATLAB. All of you can explore it, okay? Around 11 membership functions or so are there. Inbuilt membership functions are there 11. You can create your membership functions also, okay? So here there were two inputs. The first input was service, second input was food, and your output was tip. So I'll just double click on this show you. So this is my service. Okay, service, we said poor service, good service, excellent service. I have taken, you see, Gaussian membership. I can change it. I can have the Gaussian membership function. So I create a membership function with 0 and 10. You can see that. So this is what? This is good and this is excellent. Similarly, for transit food, average to generalistic, varying from 0 to 30. So, so we can say if service is for food is cheap, if service is good. If service is as many rules as you want, depending upon how many this you have. If you have 9, if you've got 3 cross 3, then you can create 9. So like that you can create, okay? And then I will show you the rules. So see. Now let's assume that we are giving some value for service. Suppose service can vary from 0 to 10, right? So I'm giving service as 6.44 and I'm giving food as 2.9. So you see here, within the maximum value, here also here, and here this is 0, this has some value. You aggregate it together, defussify it, it says the tip is 12%. Now let's just change this a little. Let's say service is also fine. Tip is also fine. How much? 15.3%. Now let's make it a very poor service. Okay. And very poor food also, naturally. It has to reduce. Very poor service, but food was good. Tip has increased. Okay. So this is how you can see the rule viewer. You can do your projects also like this. Then you can see the surface viewer, the thing that I showed in the first slide, surface viewer. So this is a surface viewer where you can see food and service and tip and trading. This is the surface viewer. Okay, so even in the other one I had created target seeking. This was the MATLAB example that I showed you, my target seeking role. This was a variable. This was membership functions that I had used. Okay. Here also you can do similar. What are some of the applications of fuzzy logic system? I'm sure most of you have seen fuzzy logic systems in different places, right? So because most of the washing machines that are available in the market, they have fuzzy logic. So what happens in a fuzzy logic is, most embedded electronics nowadays we can see fuzzy logic system. So for example, let's take a washing machine or a dishwasher. So in a washing machine or a dishwasher, what it can do is, it can sense the dirtiness of the cloth and also the heaviness of the load, and depending upon how dirty the water is and how heavy your load is, it will decide how much water has to be given to the washing machine and also how many rinsing cycles or how many washing cycles have to be given. For example, you can just use a light sensor, right? So if it is clean water, okay, then the water will be very clear. Okay, if it's dirty water, then the water is more or less like opaque, right? So a sensor can give you that value. Light sensor can be used. So depending upon if you are putting very solid clothes, very dirty clothes, okay, and then what you can do, then naturally the fuzzy logic system will decide that washing has to happen 2 to 3 times, rinsing has to happen this many times. Okay, similarly same thing with the dishwasher also. So depending upon how clean your dishes are or your utensils are, it can decide how many times the rinsing cycle should go on. So this is very common nowadays in embedded electronics, like in fuzzy logic, in washing machines and dishwashers. You can see it in air conditioners also, wherein it will decide, depending upon the outside temperature and your preference, it will set the automatic temperature for you. So fuzzy logic is also seen in a lot of embedded applications are there. Embedded system applications are there for fuzzy logic. So as computer science engineers, probably you'll be working on a lot of embedded systems, right, in future. Apart from that, it is used in traffic control, in aircraft flight control, in satellite altitude control, in missile control, in automobile speed controller, in robotic control, air conditioner control, power system control, biological process control. So almost all the real world applications of fuzzy logic along with the product and the company, so that you can appreciate the advantages and how they are using fuzzy logic. For example, the company Nissan, if you know Nissan, right? Automobile company, they are using fuzzy logic for anti-lock brakes. So it uses fuzzy logic to control brakes in hazardous cases, depending upon the car speed, acceleration, wheel speed, etc. Again, Nissan uses it also for auto transmission. Fuzzy logic is used to control the fuel injection and ignition based on throttle setting, cooling water temperature, RPM, etc. Honda is also using it in auto engine to select the gear based on the engine load, the driving style, road condition. Canon, you've all seen Canon's printers and copiers, right? So Canon uses it for adjusting the drum voltage based on picture density, humidity, temperature. Again, in cruise control, all these companies are using to adjust the throttle setting to set car speed and acceleration. That's not the list. It's a very big list. I've just taken few for you. Dishwashers, as I told you earlier, for adjusting the cleaning cycle, the rinsing and wash strategies, based depending upon the number of dishes and the amount of food served on the dishes. Elevator tours. Microwave ovens also. Then it is used in palm-top computers to recognize handwritten characters in plasma etching. So these are just few applications of fuzzy logic that you can see. There are many more applications also. Okay. So with this, I think we have come to the end slide. I'll just give you a few references that I have used. Okay. So this particular book by Timothy J. Rose, Fuzzy Logic with Engineering Apple, is a very good book. If anybody is interested to read further, please grab a copy of this from your library. It's a very good book. I think it's available to download also. These are some other references that I have used. Okay. So with this, I have come to the end of my